Hello, and thank you everyone for attending today. Welcome to the presentation that's going to be jointly presented by BISN Oil Tools, Chevron, and IPI Packers. So today, my name is Jeff Folks, and my co-presenters today will be George Farag from Chevron and Adam Ben Saeed from IPI Packers. Today here we're to talk about a novel approach, collaborative approach on abandoning wells. These were done in Australia on behalf of Chevron, performed by BISN and IPI. And the biggest challenge we were faced with were they were having shallow gas. Zone anomalies as they know it, sustained casing pressure, surface vent flow. It's known by many names around the world, but it's basically gas migration or bubbles coming up through a cemented annuli. And we're going to talk today about how we approach this a little bit differently than your traditional methods. So let's first talk about the conventional method before we get into the novel approach that we're going to speak about today. So conventional methods use long section mill windows, typically plus 100 feet or 30 meters, enable you to put a 30 meter or 100 foot cement plug in place. So section mill in these long windows takes a lot of time, generates a lot of swarf. There's a lot of disposal, so there's costs associated with that as well as HSE hazards. And there's also a lot of complications that can come along with that. So one, you can get stuck in the hole. The longer the window is, the bigger chance or higher likelihood there is of breaking the blades, sticking something in there, getting extended time, and as we all know, time is money. So after section milling this long window, traditional conventional method would be to set a mechanical bridge plug inside the inner casing. So what that does is it's very restricted. So a mechanical bridge plug is designed for a certain type of casing, a certain size, a certain weight. It doesn't have a lot of variability with it. It also has limited contact areas. You're putting a lot of stress on one part of the casing as opposed to extending that out over long regions of the casing or long lengths, which can cause potential casing damage. And you're abandoning this well, you already have gas coming up the backside. The last thing you want to do is cause more problems by damaging your casing. The last step in the conventional method is putting in cement. And we all know the downfalls of cement as a barrier material or a P&A material. It's very porous, it shrinks, it develops cracks over time, and there's typically a very long wait on cement time, between 12, 24 hours, depending on what additives you had. So as you see in the photo, you just can't trust cement. So before we go any further with this, we need to talk a little bit about the technologies that we're working with today, specifically the IPI Packers and the BISN WellLock M2M technology. So I'm going to hand over to Adam, and he's going to speak about the IPI Packers.
Thanks, Jeff. For this P&A campaign, we have used IBI Permanent Inflatable Bridge Plug, PIBB, and the plug itself consists of three main sections. The top section consists of the releasing mechanism, either lift hand thread or shear disconnect, or even by a pressure release. Then comes the middle section, which is the tool valving system. It has two spools, or we can call them even valves. The opening valve, which protects the backer from premature inflation, and also the closing valve, which shuts in on the inflation pressure for permanent seal. After backer setting, these two valves will provide a redundant seal on the inflation pressure for permanent abandonment. The third and the last section of the tool, which is the backer element, it's 1.6 meters in length, and its construction features DuraGrip external anchoring band, the band which we can see on the drawing on each side of the backer element. And this DuraGrip is designed to maximize anchoring for optimal differential pressure holding capability while maintaining an effective bidirectional seal. Unlike the mechanical backers, which is casing specific, IBI inflatable backers covers a wide range of casing internal diameters. It can be ran and also retrieved through restrictions as the backer itself retracts to its original OD after deflation.
Thank you, Adam. So you've heard a little bit about the IPI Packers. The next step, or the other material that we're going to be using this as a novel approach, would be the bismuth alloy plugs provided by BISN. So I said bismuth alloys because we do use bismuth as the main component of these different plugs, the alternative to cement. And some of the unique properties of bismuth is it's a eutectic material, meaning it solidifies and melts at basically the same temperature, a very sharp melting solidification point, meaning it's either solid or liquid. It doesn't go through the gel phase. Also has a viscosity very similar to water and has a very high density with a specific gravity of 10, so 10 times heavier than water. The combination of those two allow us to run these tools on electric line. You don't have to pump, you don't have to displace. You can go out there with a wireline unit, again, saving cost, less HSE risk, less personnel on location, and then run these plugs and create these gas tight barriers. They're corrosion resistant, not affected by H2S or CO2, and probably the best quality is they expand like water when it turns to ice when they go from a liquid back to a solid. So remember we talked about the cement, very porous and shrinks on solidification. Bismuth alloys actually expand on solidification and have zero porosity. The way we get these from a solid to a liquid then back to a solid again is we melt them down whole using an exothermic chemical reaction, modified version of thermite, as you can see there. So the best way to describe the BISN tools is like a big candle. The way they're constructed is we have our chemical reaction heater, and then we cast a bismuth alloy on the outside. You can see in this video, the part sticking up is the heater, and the alloy is the silver part that's on the outside. This is in a piece of glass casing, so you can actually see how one of these tools would set down in your well. So it's like a big candle. The heater is the wick, and the alloy is the wax. What happens when you light a candle? As you can see, the heater starts burning down just like the wick of a candle. Then as it reaches the top of the alloy, that alloy begins to melt and drip down the side of the candle. You'll notice that all of it doesn't run to the bottom. A lot of it stops on the side of the candle, or on the side of the tool, just like a candle would. That's that eutectic property, making it solidify very quickly. It then continues to burn down, continues to remelt until you have all of the alloy left at the bottom of the heater, and that's where your plug is actually being formed. So in this particular video, the heater is still in place, as you can see, but for our P&A plugs and what we did in all of these wells for Chevron, we actually extract that heater out of the core when it's in the liquid form, leaving a solid alloy-only barrier, meeting the NORSOC D10 requirements of a single material plug. Now that you know about the two materials, the technology we use for this campaign, let's talk a little bit about the campaign itself. So this was done for Chevron, as you're probably aware with George being here, on the Australian Northwest Shelf. So it was a total of 34 wells during this campaign. There were 19 onshore wells, and we say onshore, they actually were more like offshore wells because they were on a remote Thevenard Island. That was basically the logistics were like going offshore as far as getting all personnel and equipment out there. And then another 15 wells on a platform. Each one of these had zone anomalies and gas migration coming through them. They had limited success in previous campaigns in going out with the conventional method that we spoke about earlier. So they chose BISN and IPI to try to optimize the P&A solution and come out with a better result of actually stopping this gas migration. So now next we'll talk about the method itself and how we actually got to this solution. So we've talked a little bit about the BISN technology itself. We've talked about the IPI packer and the conventional method. We've also in the previous slide gone over what the program looked like as far as the campaign itself, how many wells, where they were, what the problems were. So we're going to talk a little bit about the alternative method that we're talking here. And as you can see on the left-hand side, this is just a schematic representing cemented annuli with the red lines running through it are just gas that's percolating through the cement, basically what we're here to address. On the right, you'll see it is a section mill, much like the conventional method. However, unlike the conventional method, this window is significantly shorter. We were able to reduce that from a minimum 30-meter window down to a 6-meter window. That 6-meter window was enough to accommodate the IPI packer and the much shortened BISN plug, which is 1.5 meters compared to the 30 meters of cement required for the conventional method. So with that, I'm going to hand back over to Adam to talk to you a little bit about the IPI packer itself.
Thanks, Jeff. As it has been mentioned earlier, unlike the traditional method of milling a long section window, then set a cement bridge plug, this collaborative approach which we have used for this campaign requires a window of just plus minus 5 meters. Then the inflatable backer can be deployed on drill pipes at the bottom of the section milled window. Then it can be inflated from surface by applying the required pressure sequence. Once the backer is inflated, we can verify if it's fully set and anchoring by picking up and slacking off weight. And once the backer setting indications are verified, then we finally can release the drill pipes from the backer by rotating the string. We also have the option to deflate the backer prior to disconnecting from the drill pipes if it was, for example, set at the wrong setting depth or for any unforeseen operational reasons. This can be achieved by applying the required pressure to activate the emergency deflate system and deflate the element pretty much. After deflation, the backer element will retract to its original OD and it can be retrieved to surface through the section milled window or through any restriction.
All right, so the window has been cut. The IPI packer has been set inside that window, as you've seen. The next step was to take bismuth alloy beads and drop them down the well on top of the IPI packer. So this does a few things. One, it fills in the void. So the IPI packer has quite a bit of long fishing neck. And so what we want to do is maximize the alloy we send down in the plug to make sure it's all forming the plug and we don't lose any of that down around the fishing neck of the IPI packer. Second, it protects the IPI packer. So having that standoff there ensures that none of this liquid alloy, which is quite hot, is going to get down to the element and potentially damage the element itself. With the bismuth alloy beads in place, on electric line, we run in with the tool. Again, this is the construction we talked about with the chemical reaction heater and the bismuth alloy cast on the outside of it. We just run down and set it directly on top of the bismuth alloy beads that we have put in place inside the window, milled section window area. Once the tool is in place, you activate the electric line. 240 volts, pulls about 60 milliamps, only need about 15 seconds of power. And then that will melt all the bismuth alloy just like you saw in the video. It will collect around the bottom of the heater. And in this case, as you can see here, we have extracted the heater. That's that black section that's being pulled up into the casing from the plug itself. And you're left with a solid alloy plug covering the section milled window. So a little recap, we were able to successfully reduce the section milled windows. I did not mention this earlier, but we reduced them from 100 foot down to 20 feet. That's 30 meters down to 6 meters. The reason we were able to shorten it so much is instead of a 30-meter cement plug, we only needed a 1.5 meter bismuth alloy plug. And again, this is the acceptable practice as was accepted on a recent campaign in Norway by the PSA, Petroleum Safety Authority, according to the NORSOC D10 standards. So significant reduction in swarf by shortening that window. And overall, it was a big success. So the IPI packers were all set and tested in each of these wells. The BISN well lock M2M plugs were tested. This was both a positive and a negative inflow test on each plug successfully. And the shallow gas was isolated in each one of the wells. And as you can see in both of those photos, that's a big thumbs up. And we got a big thumbs up from Chevron, as I'm sure George will attest to. We really appreciate all your time for viewing this presentation and look forward to answering any questions you may have. Thank you.